Okay, let's start. So I put up some screenshots from Arten's algebra book on Jordan. But it's very interesting what he says, which becomes clear if you try to read um, this Perkos book. Perkos has some discussion on how to actually go about computing the Jordan canonical form given a matrix. Now there are two things. One is uh, trying to see at the end of the day, if you have a matrix, the claim is that there is a P such that P inverse AP is of a certain form. Now, it is not that difficult. It's quite easy to guess what that form will be, what the Jordan canonical form, what is it going to look like. But that is not quite the same thing as saying I know the full the P. You know A, you know what form it's going to take, but you may not know P. To compute P is the same thing as computing a generalized basis of eigenvectors. That is a very painful task. I mean, yesterday I thought of putting up an example, but even that example, it's not. If you have to do it, you will go through it. Let me put it that way. But for most proofs, it's enough to know what form the Jordan canonical form can take given a matrix. So what do we mean by saying that what form can it take? After all, let's take the case of real eigenvalues. We know that the Jordan canonical form is composed of these blocks, what we call Jordan blocks. 1 by 1 would just consist of lambda. 2 by 2 would be lambda 0, 1 lambda, and so on. So for each size, there is a specific Jordan form. Then it just becomes a question of how many there are of each size. How many 2 by 2 blocks are there? How many 3 by 3? How many 1 by 1? And so on. Once you know that, you know the full listing. Same with complex eigenvalues. So that's just a numerical question, and that is also done in Perco. You can have a look. That's most cases that's enough. You wouldn't actually need to know what P is. But if you are solving a differential equation explicitly, then you would need to know P after all, right? I mean, if you want a concrete answer, you would need to know P. So it depends on the setting. In any case, without, I mean, it's a silly question to ask somebody to compute the Jordan canonical form of a complicated even 4 by 4 matrix. There's no point. It will take time, whatever you do in general. So at most we'll be dealing with, if I'm going to ask you, it will be 3 by 3. Or if it's 4 by 4, it will be very special. So even without knowing any general procedures or algorithms, you should be able to do it. That's the idea. But what I would like to say is that one theoretical point, which you'll know if you study the proof, I would strongly advise all of you to go through the proof. The proof is quite interesting by itself. And it's related to some basic theorem in algebra actually, not just linear algebra. Now the thing is that right, the main idea in that whole proof is that this is the first screenshot in the two that I posted. The Now I forgot what I called this highest power. No, we didn't give it a name. We had the multiplicity of lambda, but the power which will make a minus lambda I times some power times v equals 0, that was not given any names. Let's just call it exponent r. We know that this exponent is by definition less than or equal to the multiplicity of lambda for sure. So a minus lambda I to the power r acting on v is 0, but any lesser power is not 0. This generalized eigenspaces that we corresponding to a lambda that we have been talking about. How does one go about? Yeah, so the main idea is just that if you look at the set v a minus lambda I v etc., and this set is linearly independent, and it forms a basis. So you take the span of this. By the way, anything in the span of this is again a generalized eigenvector, because if you multiply that by a minus lambda I to the r, it will be 0. So this particular set is span S, and span S is invariant under A. This is slightly different from saying that, see, in the class I proved that this, what I call generalized eigenspace, for the same lambda, for instance, there could be other vectors W which are generalized eigenvectors, which may not belong to this subspace, right? So this is something more, even smaller subspace compared to. But these are, at the end of the day, these are the things which are going to give rise to Jordan blocks. That is the basic thing, observation. So each of these subspaces, the whole proof builds upon that. You want to decompose whole vector space into sum of subspaces like this. Take a vector, one vector V, form this corresponding S. This proposition says it's invariant. That proof is something we have done. It's invariant, and this set forms a basis. So the moment you know it forms a basis, you can immediately see what the matrix is going to look like in this. If you think of it as a linear transformation, A will take S back to itself, span S back to itself, because it's invariant. And in this basis, it's precisely going to look like the Jordan block. That's where that specific form comes from. You can see, but that part of the exercise is easy. The difficult part, which would require a bit more work, is to see that the whole vector space can be written as a direct sum of these things. And the proof proceeds by induction, basically. If you have a subspace invariant under A, dimension of a vector space. So if you have a subspace invariant under A, You restrict A to that. Then you assume that on that restriction you have the Jordan form. And then you have to, yeah, it's an interesting proof, but the starting point is this. These are the things which will give rise to those Jordan blocks. And that point that I just made, that you can, for a single lambda, you can have different generalized eigenvectors V and W, right? So if that happens, you'll get different blocks. That's it. After all, there's no guarantee that for given a lambda, there's only one block. It can repeat itself, different sizes also. So, but again, the actually computing this generalized basis consistent of generalized eigenvectors is quite messy and can be done. If it were just for this kind of thing, it's okay. I mean, you just keep on taking powers and multiplying. Even that, if you do it by hand, you can quickly imagine that it's very unpleasant. Taking powers of a matrix already becomes something. But at least this gives, you know, that this is a basis. But the problem arises when you have to compute all possible generalized eigen. There will be several corresponding to lambda. I might come back to this and put up another short video. Oh, by the way, I put up a video on that variation by parameters, the inhomogeneous system case. Here, there's not much to say. I mean, it's quite straightforward. You have a look at the video and the notes. Now, now we sort of now we are done with the linear case. We come back precisely to the point where we had stopped when we were talking about nonlinear system. The last topic we had discussed there was flows, invariant subsets under the flow. Yeah. Well, the chapter next to that, the section next to that was linearization. Obviously, since he did linear equations first, that order makes sense. But since at that point we had not even talked about linear equations, linearization doesn't hold any much significance there. So now that we have done that, the linear constant coefficient case, we can go back to, this is a very powerful idea in various aspects of differential equations, not just ordinary differential equations, even in very complicated partial differential equations. So now it's section 2. So we are back in the general case, x dot equal to f of x. As always, we have an open set and a C1 map. And we have a point inside that. Now, I'll make a whole bunch of definitions. Basically, they're just carrying over whatever we have done in the linear case to this general setting. So the first thing we need is the notion of an equilibrium point. X naught is an equilibrium point. as I've been repeatedly saying, these are very significant. So one would like to understand what solutions look like when we are close to this equilibrium point. So if I start at some other x naught prime close to x naught, am I going to move towards x naught or away from it and so on? The linear part, now in the second definition, I'm already assuming x naught is an equilibrium point. F of x naught is 0 is the function x going to ax, where a equal to df x naught. This has nothing to do with differential equations. I mean, whenever you have a C1 function, you can talk about its linear part. And why do we call it the linear part? So the linear part of a function is of a function f is ax is what I'm saying. So ax, where a is the derivative of f at x naught. So why would we call this the linear part of f? Well, it comes from Taylor series, that's all. After all, we know the Taylor series in multivariables, which I don't think I discussed, but it takes this form, x minus x naught. If I assume even C2, then one has what the so-called matrix of Hessian matrix, which consists of second order partial derivatives of f. Here I would do x minus x naught on this side and x minus x naught transpose when I'm on this side, plus small o of norm x minus x naught cubed. No, not small o, big O. I mean, I need not have actually taken this second order term. I'm just writing that as a piece of general information. That's all. That the Hessian matrix, multivariable, this thing. By the way, this thing that I've written here is for f from Rn to R, not quite f from Rn to Rn. Huh? Sorry? Yeah, thanks. This should be half times this. And this is for a function from Rn to R. Not Rn to Rn like we have here. If you have Rn to Rn, of course, you can do it for each one separately, each component function, and write a similar thing. But the upshot is that these after this df x naught, x minus x naught, everything else depends quadratically or higher on this x minus x naught. Here already for the Hessian, it's second order. X minus, it's, if you take the norm, it will be less than some constant times x minus x naught square. This, so the first order expression in x minus x naught is, you have to stop here. It would be this entire thing. This, but since I've assumed that f of x naught is 0, this term doesn't appear. So the linear part is just this. X going to x is precisely this function. So that's what we have. So if you replace the function f of x by its linear part, that's ax, you get a different ODE. That's called the linearization of the original one. The hope is that this, when we do this, in some cases, by studying this, x dot equal to x, we should be able to get some information about the original one, which on the face of it seems like a big hope. I mean, this function f of x might be extremely complicated and so on. How would replacing it with a constant coefficient linear system help us get any information? But surprisingly, it does, at least under a very important assumption, which I'm going to define next. So this assumption is crucial for if you want to use the linearization technique. The assumption is that x naught is a hyperbolic So the assumption is that all eigenvalues of A have either negative, strictly negative or strictly positive real parts. So in other words, from our earlier language, the central subspace is the central subspace is trivial. So this assumption of a hyperbolicity, if you ever look at dynamical system, this notion is very important. I mean, very important in the sense that when you make this assumption, lots of theorems can be proved. But then the question becomes, theorems can be proved, but how realistic is this? In the, after all, differential equations have applications. In applications, is it a realistic thing to say that it's hyperbolic? But in it's that seems, I mean, that's a separate question, but from a mathematical point of view, this condition is not unnatural, in the sense that if you look at all the set of all matrices, Generically, you would expect all first of all, generically, you would expect all eigenvalues to be non-zero, because what does it all depends on what you mean by generically. But the point is, the set of matrices with at least one zero eigenvalue is a much smaller set than the all matrices. That's one thing. Same thing with zero real part. If you look at matrices, the set of matrices with zero real part is a much. It's like a small, not a subspace. It's called what is called a submanifold, something like a submanifold, which is basically a smaller dimensional set inside this huge Euclidean space. This puts a strict condition on that, and that will cut down the dimension, basically one dimension lower. So in that sense, if you pick a random matrix, it's more likely than not that you'll hit something like this, that it has eigenvalues are all strictly positive or negative. But that's not really a good reason. I mean, that's a very abstract reason. In practice, whether this condition is realistic is more important to me. But that I have nothing to say, since I haven't looked at that aspect of the story. But one sees this assumption often, that one studies this dynamical system under the hyperbolic condition. The next one is, of course, something we had already seen. X naught is a sink. We'll say X naught is a sink. If all eigenvalues of df x naught have negative real parts, and otherwise you'll say it's a source if all eigenvalues have positive real parts. The hope is that under these, just knowing the eigenvalues, we should be able to say that if this is x naught, in the sink case, all trajectories should, at least close to that, should move towards that. In the source case, they should all move away. That's a hope, at least. Now, this definition there's some slight ambiguity. When it's a source or a sink, then of course it's clear that it's hyperbolic. But when you say it's a saddle point, I think it's still assuming that it's a matter of definition. You still assume it's hyperbolic because anyway the theorems are proved under the hyperbolic assumptions. Though the definition doesn't explicitly say that. So here some trajectories might move towards that, some might move away. Relation with flows. So here's a small proposition. X naught is an equilibrium point if and only if it is a fixed point of the flow Pt, i.e. Pt x naught equal to x naught for all t in R. So already I'm making an assumption that all flows are defined for these flow maps are defined for all time. So in other words, every solution is defined for all time. So that's going to be a standing assumption. Otherwise, as we saw, it becomes a bit messy. You have to pick out you can't quite work with the whole open set U. You have to pick out a subset of U cross R and so on to even define this Pt. So we'll assume that it's defined for all t. And then the definition of a fixed point is just that you would have seen fixed points in other settings, metric spaces and so on. It's just that Ptx naught. So why is this the case? Well, it's just we go by the definition of the flow. Now, what is Ptx naught? By definition, to find out Ptx naught, you just start at x naught, look at the solution starting at x naught, travel along the solution for time t, see where you land up. That's Ptx naught. So we had a notation for this, right? I think at various points I used u, t comma y and so on, where the second coordinate denoted the starting point of the solution. So let me go back to that. So this notation uty was used earlier. It means u dot equal to f of u0 equals y. So with this notation, phi tx naught is u t x naught. This for all t. From this, how do you conclude that f of x naught is 0? Any suggestions? Differentiate with respect to what? Time. So just take the derivative of this, the solution, with respect to time. Or let me put d by dt, that's fine. D by dt and the right hand side doesn't depend on time, so I get 0. But what is the left hand side? Derivative, time derivative of u. By definition, that's after all u is a solution to the differential equation. So d by dt of u is f of u. By the way, where would I take the derivative here? I mean, this is true at whatever point because it's true for all t. But if I want to use this, at what t would I take the derivative? At 0. 0, because the initial point, it starts off at x0. See, u0y is y. So I would take this at t equals 0. So at t equals 0, I get f of u of 0 equals 0. But f of u of 0 is f of x0. And you have what you want.
While back, you said something about if the flow is not, if the solution is not defined for all time t, then we do something like rescaling.
Yeah, correct. That's right. Yeah, that's actually theoretically one can do that, though it's again something which is not practically that helpful. That I think that point about rescaling was made only to say that even making this assumption that the flow is defined for all time, you don't lose much, is what he wanted to say. Even though if you want to do for a given differential equation, if you want to do that, it's extremely messy. So that's why I didn't sort of dwell on that too much. So in most cases, even without the rescaling, it will be clear that the flow is defined for all time. The converse is even easier actually. Suppose I know f of x naught is 0, but you can't retrace your steps like this to get the converse. You have taken a derivative at a specific time. That ruins things. So if you want to, you have to use a different argument. So suppose f of x naught is 0. I want to conclude that pt x naught equal to x naught for all t. How do I do this? This I think I already told you this in a different form. Again, it's a matter of what is pt x naught.
So we can consider, we can use uniqueness of solution, and then we can consider the unique solution x0.
Correct. So this is just a simple consequence of the uniqueness of solution. The fact that f of x naught is 0, this implies that if I define a solution by x of t equal to x naught for all t, this is a solution. And since it starts at x naught, it's a unique solution. Now, why is this a solution? Well, you just differentiate x dot t. So this is a solution if and only if x dot t equal to f of x but x dot t, from the way we have defined it, this is 0. X of t, again from the way we have defined it, this is x naught for all t. So this is f of x. So the fact that this is a solution is a restatement of the fact that f of x naught is 0. So therefore, ut x naught equal to, by uniqueness, yeah, this is a solution. By uniqueness, this is the only solution, and the ut x naught is equal to x naught. So depending on the context, you will call it either an equilibrium point or a fixed point. When you're talking about flows, one thinks of fixed point for a flow. In the context of the original system, you would say it's an equilibrium point, especially when talking about phase port rates and so on. So here's an example. So that will there are several very important theorems in this chapter, but all of them are quite involved, more involved than what we did when we talked about nonlinear systems. So I won't cover them, but I will state them and explain them in detail. Then we'll move on to something which we can actually go through the details without much problem. It is this very classical method of finding out what kind of equilibrium point we have without actually computing eigenvalues, called Lyapunov functions. This is used in physics a lot. Oops, sorry. Excuse me.
No. Oh, it's the
So let's take this nonlinear system where f of x, so it's a 2 by 2 system. F of x is x1 squared minus x2 minus 1, and the second coordinate is just x2. This has two equilibrium points, f of x equal to 0 at x equal to 1, 0. So x1 is 0, x2 is, yeah, okay, and the other one is, and minus 1, 0 as well. And the derivative, so at the first, at 1, 0 is this matrix. this. So in the first case, I get so this 10 is a source because I have two positive eigenvalues, and this I have one positive and one negative, so this is a saddle. But more interesting is I said that there are some non-trivial theorems. One of the non-trivial theorems is this Hartman-Grobman theorem, which says that when you have a hyperbolic equilibrium point, you draw the phase portrait. What it says is you can find a one-to-one continuous map with continuous inverse from a neighborhood of that point to some open set in Euclidean space. Now, so that when you consider the linear system, corresponding linearization of this on the target, you will again get a bunch of trajectories there on the target. So this map will take curves here to curves here. So the phase portraits are going to look similar. Perco is a bit sloppy here, I will just mention. So it will be proved this has nothing to do with saddle or source. It's a statement about hyperbolic, that if x naught is hyperbolic, then there exists continuous one-to-one map H from a neighborhood of x naught, epsilon neighborhood of x naught. That's the ball of radius epsilon around x naught onto an open set V. So this will be open. With H inverse from V to this is also continuous. So such a thing is called a homeomorphism in topology. Yeah, Perko is sloppy in the sense that he says, which transforms the given equation, which is x dot equal to f of x, to x dot equal to a of x. Now how would you interpret transform? The simple naive interpretation is, if you have a solution to the first equation, if you apply h, you should get a solution to the linearized one. What is the problem with that? So here is x of t, h is taking it to something else. So I'll get h of x of t in the new curve. So here I have x dot equal to f of x, here x dot equal to ax. What is the problem with taking h of x of t and asking if it's a solution to x dot equal to ax? You have to look at what we are asserting about h a bit carefully. What do we know about h? Well, it's also one-to-one and it's a homeomorphism essentially. So what? What's the problem? Differentiability. So no, not quite. That's it's not asserted. Actually, this is not there in the actual theorem. What it says casually here, that the equation gets transformed, is not part of the Hartman-Grobman theorem. It's a very delicate matter. This is called a conjugation of two dynamical systems. It says that one picture is same as the other picture. It's a very delicate matter how smooth you can take H to be. Even for changing from continuity to something slightly better, let's say Lipschitz, will require a lot of work. Certainly not, you can't say that you can choose H to be C1. These things are not evident at this stage, why it's a big deal, but the proofs will show that. H, so I won't write the transform business, but what is true is that the trajectories are taken to other trajectories. So this smooth curve is taken to this smooth curve. From that, unfortunately, we can't say H itself is smooth. That's the only problem. You can have a continuous function which will take smooth curves, certain smooth curves to certain other smooth curves. So you can see the level of subtlety which is required here. So H takes trajectories of x dot equal to f of x to, I mean everything locally, by the way. It's only all the attention is confined to n epsilon x naught. So outside that, H is not even defined. To trajectories. Trajectories means solutions. As sets.
It may happen that different points are mapped to different points. I mean, different times of solution.
Yeah, the time parameterization may not be maintained. Correct. That is precisely the point. It may do some stretching, contraction, but net result is this piece will go to this piece. It's not like you're moving it in a very respecting time. Yeah, if this statement that I had made here earlier, h of here it is time is taken into account, x of t and h. So this h that we have does not care of, is not going to care about that. It will mess up things. So in particular, this h of x of t may not even be a solution. Its image as a curve will be that of a solution, but its own as a function, it will not be a solution. H is also going to respect orientation. So if something is going to yeah. If something is going to move away from the origin in one picture, and if I take H of that solution, that will also move away from the origin. Something is going to come towards origin, that will also. So from a picture point of view, H is good enough. Whatever picture that you get on in this linearized thing is going to completely convey what is going to happen here. You can move back and forth between these two by H and H inverse. But as I said, you may not get literal solutions when going from here to here. And okay, so we'll stop here. So the same example that we just did, this f of x equal to this, for this one can actually write down an explicit h which will transform it to, but in this case h will be actually smooth. So things work out well. So you will, everything is can be seen there. So I'll do it next time. Okay, let's stop here.